Hi all, welcome to the next topic of Unit 3, Computer Arithmetic, the floating point multiplication. So coming to the contents, in today's lecture we are going to discuss about an introduction to floating point multiplication. What are the steps of floating point multiplication algorithm along with its flowchart. So coming to the introduction, the floating point multiplication algorithm is comparatively easy than floating point addition and subtraction algorithm, but it consumes more amount of hardware than fixed point multiplication algorithm. So the amount of hardware or the amount of registers which are required during the floating point multiplication is more compared to a fixed point multiplier circuit. And moreover, the multiplication of a two floating point numbers requires you have to multiply the mantissa part of your data and then add the exponents. So and in this particular algorithm, you don't require any comparison of the exponents or alignment of mantissas and all, like how we have done it in case of a addition and subtraction algorithm. The only thing we have to do is we have to multiply the mantissa part of your floating point data and add the exponent part to get your product of your floating point multiplication. So coming to the steps of floating point multiplication algorithm, it is divided into four parts. Check for zeros, add the exponents, multiply the mantissa, and normalize the product. So there are four steps. Checking for where you are going to check the operands for your zeros in the first step, and second part you are going to add the exponent part of your data, and next you are going to multiply the mantissa part of your data, and finally the result has to be normalized using a normalization technique. So the first step is a check for zeros. So as we know, uh, in the multiplication we have two operands where one is said to be called as your multiplicand and the second one is said to be called as your multiplier. So internally in your hardware we have BR and QR registers, where BR register is used to store your multiplicand and QR register is used to store your multiplier. So here I am considering two operands where my value of my BR register is 0.582 and 2 into 10 to the power of 5. QR register is 0.234 into 10 to the power of 7. These are my two operands. So in the first step, we have to check if any of the operand is a 0. So if in case of a multiplication, if any of the one operand is a 0, obviously the product becomes 0 because we are performing a multiplication operation. So if BR or QR operands contains a 0, then obviously the result which has to be stored into the AC register, it becomes a 0. If both the operands contains a non-zero values, then we move on with the next step. So in this particular example, both the BR and QR contains a non-zero values. So we continue with the next step. So the next step of a multiplication algorithm is adding the exponent part of your data. So as we know, the floating point numbers are represented in the form of m into r to the power of e, where m represents the mantissa part of your data and r represents your radix and e represents your exponent. So if we consider this floating point number, 0.5812 is nothing but your mantissa part, whereas your 10 is your radix part and or base, where 5 is your exponent part. So in case of a multiplication algorithm, when you are performing a floating point multiplication, so you have to add the exponent part of your data. So there is no need to align the mantissa here. We need to just add the exponent and this exponents will become the resultant exponent. So say for example, I have two exponents where my BR register, it is having an exponent of 10 to the power of 5, where my QR register is holding an exponent of 10 to the power of 7. So it is in the form of a power m into a to the power of m. This is my exponent of my first operand and this is exponent of my second operand. So in multiplication, I have to add the exponents and this becomes the resultant exponent. So a power m into a power n can be done as a to the power of m plus n. So I am going to add my exponent part of the data. So 10 power 5 into 10 power n, I can write it as 10 to the power of 5 plus 7, which is equal to 10 to the power of 12. So this will become the exponent of my resultant product. Okay, so I'm not going to do anything with respect to mantissa in this step. I'm just going to add the exponent part of my data. And you need not have to do any alignment of your mantisas or in such a way that the exponent has to be equal the way you have done with addition and subtraction. The only thing we have to do is just add the exponent part of your data. And going for the next step, you need to multiply the mantissa part of your data. So here, to perform a multiplication of the floating point numbers, you have to implement the concept of sign magnitude multiplication to perform a multiplication of your mantissa part of your data. So in the if you consider these two as your operands, in this particular adding the exponent, you have added the exponent part of your data and got your resultant exponent. But when you want to multiply these two mantissa part of your data, then you have to implement the concept of sign magnitude multiplication flowchart. So we have already discussed about sign magnitude multiplication. So this is a flowchart for a sign magnitude multiplication. So we have to implement this particular flowchart to perform a multiplication of a mantissa part of your floating point data. Okay. So at the result of the multiplication of sign magnitude, you will get your product of the mantissa part stored in a register AQ. Okay, so the product of this multiplication of the mantissas of a floating point number will be stored in a register AQ. So the next step of the multiplication is to normalize the product. So you have got a product which may be in a normalized form or it may not be in a normalized form. So you have to check whether the product is in a normalized form or not. If it is in a normalized form, there is nothing to do with it. We can proceed. But if the product is not in a normalized form, you have to normalize the product. So consider the product. What we got is 1.0101101 into 10 to the power of 12. So this product has to be checked in order to determine whether it is normalized or not. So how do you determine a product is in a normalized form or not? So based on the MSB bit of the mantissa part of your product. So if you see this product, this particular digits after the point, we consider it as the mantissa. And the most significant bit of the mantissa, if it is a 0, we say that there is an underflow situation. So it means that the product is not in a normalized form. In the multiplication algorithm, there is no possibility of an overflow. So you need not have to check the overflow condition. But there is a possibility of an underflow which is checked by looking at the MSB bit of the mantissa part. So if MSB is 0, it means there is an underflow situation. It means that particular product is not in a normalized form. So in that case, you need to normalize the product. So for performing a normalization, you have to perform a shift left on the mantissa part of your data and decrement the exponent by 1. So when I perform a shift left operation, this 0 will go this side. So it becomes 0.101101 into 10 to the power of decrement the exponent because you are performing one bit left shift. So it becomes 11. So this particular result is said to be in a normalized form because the MSB bit of the mantissa is a 1. So this is how you normalize the product. Now let us see these 4 steps with the help of a flowchart. So this is a flowchart of a floating point multiplication where we have two operands, the multiplicand and multiplier. The multiplicand is stored in a register BR, whereas your multiplier is stored in a register QR. So the first step is check for zeros. We are checking if any of the operands BR or QR is a 0. So whenever, say for example, I'm checking the operand BR. Suppose if BR is a 0, so if you multiply anything with a 0, even though you have a QR and non-zero value, the result becomes a 0. So if BR is 0, automatically the AC becomes 0. There is no need to check the value of QR. So if BR is a non-zero value, it contains some value, then we again go for checking the second operand, QR. If QR is equal to 0, again, then the result also becomes 0. So if any of your operand is a 0, the result will be set to 0. Say if both the operands contains a non-zero values, then we go for the next step where you need to add the exponent part of your data. So the exponent of BR will be stored in a register B, whereas the exponent of QR will be stored in a register Q, small q, right? So but we have an adder In the hardware implementation, we have a hardware present only between adder, the parallel adder, which is present only between the exponents A and B. So what we are doing is we are just transferring the contents of the multiplier exponent into the a small a register, and then you are performing an addition operation on the contents of small a and small b. Now small a contains the exponent of multiplier where small b contains the exponent of the multiplier. Now you can perform an addition operation using a parallel adder on the two exponents. Because why we are transferring it from small q to a is we don't have a internally in your hardware there is no parallel adder present between q and b. So that is the reason we are transferring the contents of small q into small a and then performing an addition of exponents of a plus b using a parallel adder. And the resultant exponent becomes this whatever is the result that becomes a resultant exponent of your product, and that is stored again into small a. So this is adding the exponent part of your data. So once you are done with adding the exponent, the next step is to multiply the mantissa part of your data. So for multiplying the mantissas, we are going to make use of a sign magnitude multiplication flowchart. So that is present in the figure 10.6 according to your syllabus. So they have mentioned it as figure 10.6, but we have to implement the flowchart of this sign magnitude multiplication in order to perform a multiplication on a mantissa part of your floating point number. Okay, so once you complete the multiplication of your mantissa part, your product will be stored in A and Q registers. AQ. So your product will be stored in AQ registers. By looking at the product which is stored in AQ registers, we are going to perform the next step, which is called as a normalization, where you are going to normalize your product. You are going to check if the product is in a normalized form. If it is a normalized form, then simply you're going to end the process. If the product is not in a normalized form, then you have to normalize it and transfer it into the register AC. So for that, I'm going to take the contents of A and Q registers and I'm going to check A1 bit. The most significant bit of contents of the register A it is represented by A1. So if A1 bit contains a 0, it means that the product is not in a normalized form. So to normalize the product, I am performing a shift operation on the contents of A and Q registers and decrement exponent by 1. So when you are performing a shift operation, you have to decrement the exponent by 1. So what after performing a shift left operation and decrement the exponent by 1, your product will be in a normalized form. Now this particular product, normalized product which is present in AQ register has to be transferred to AC register because your product of your floating point multiplication has to be stored in a AC register. So you are transferring the product from AQ to AC. Now the result of your product will be stored in a AC registers. So this is a flowchart of floating point multiplication. So the two operands are checked to determine if the contain is 0. If either of the operand is equal to 0, the product in the AC it is set to 0 and the operation is going to be terminated. If none of your operands is equals to 0, then you are going to continue with the process of exponent addition, the next step of your algorithm. So the exponent of your multiplier is in small q and but there is an adder which is present only between a and small b. So it is necessary to transfer the exponent from small q to small a and then add the two exponents a and b and transfer the sum into back into a. So the next step is the multiplication of your mantissa part. So the multiplication of a mantissa part, it can be done with the help of a fixed point multiplication algorithm, or we also call it as a sign magnitude multiplication algorithm. So once you're done with the fixed point multiplication algorithm, the product will reside in the registers A and Q. But in case of a multiplication algorithm, there is no possibility of an overflow to occur. So you need not have to check for an overflow condition. But there is a possibility that the product might have an underflow situation. So we need to check the most significant bit of the contents of a register A, which is represented by A1. You're going to check it. If A1 bit is a 1, it means that the product is already in a normalized form. If it is a 0, then the mantissa which is present in A and Q register, it has to be shifted towards the left and the exponent has to be decremented. So, although the low order bits of the mantissa is stored in a queue, we do not use it for a floating point product. So, once you have done the normalization part, whatever is the result that is product that is stored in AQ, that is transferred into AC register, and that is taken into account as a product. So this is a algorithm for a floating point multiplication. Thank you.